Warning: this video was created for educational purpose. The main goal is to provide scientific and public health related information in an understandable, easily digestible manner, with a portion of humor. Might contain disturbing disease-related images and information. Hello and welcome. In today's video we'll have a look at limb transplantation and briefly touch upon replantation. Right in the end of this video, an interesting fact waits for you, so stay tuned. The loss of an extremity is a disastrous injury with tremendous impact on a patient's life. Current mechanical prostheses are technically highly sophisticated but only partially replace physiologic function and aesthetic appearance. As a biologic alternative, approximately 70 patients have undergone allogenic hand transplantation to date worldwide. To quickly elaborate, allogenic simply means the donor and the amputee recipient are two different persons. While outcomes are favorable, risks and side effects of transplantation and long-term immunosuppression pose a significant ethical dilemma. Over the past 20 years, significant progress has been made in upper extremity transplantation, although a number of challenges remain, including how to best document and share outcome measures, optimize immunosuppression, and diagnose and treat rejection. In other words, a repeated loss of freshly transplanted tissue, organ, or limb. For better insight, let's have a look at this publication by Mendenhall and co-workers, published in 2020 in the American Association for Hand Surgery. Since first hand transplantation, performed in Lyon, France 2 decades ago, hand and upper extremity transplantation is the most common vascularized composite allotransplantation, in brief VCA, performed to date, with roughly 150 upper limb transplantations in 100 patients to date in 45 centers worldwide since 1998. Hand or arm transplantation process consists of many key phases, such as patient selection, patient evaluation, preoperative planning, which includes surgical plan, team selection, role assignment, donor screening. For donor screening, it's most important that the donor must be located at a 2-hour air travel distance, no longer than that, to well preserve the limb to be transplanted. Follow-up protocol, including frequent physical exams, skin biopsies, imaging, and lab monitoring for rejection. Postoperative rehabilitation, which includes physical therapy and outcome measures. Most importantly, motor function and sensory function. And if you want to know more about donors for such surgical procedures, those are mostly shortly deceased individuals that gave their donor consent for further medical use of their bodies after death. And well, the question still remains, why transplantation of a limb, such as hand or entire arm, foot or an entire leg, still remains a challenge when compared to a more conventional transplantation of an organ such as liver, kidney or lung. And the answer is, limbs have a slightly different immunologic profile compared with solid organ transplants due to their composite tissue, which includes bone, tendon, nerve, muscle and skin, which is known to be highly antigenic. In other words, highly antigenic means skin has the most potential to elicit an immune response, increasing the likelihood of a transplant rejection. To summarize, the high degree of complexity of a transplant graft increases the complexity of inevitable immune suppressive therapy. With respect to this, since 1962 until today, the literature continues to support that replantation is the best method to restore function to an amputated extremity. Recently, a novel biotechnological approach provided change of game plan for future developments in the fields of surgical procedures for limb transplantation. What this scientific group did, in brief, was using fresh amputated cadaveric mouse and primate arms in a so-called perfusion decellularization process. This simply means native veins and arteries were used to infuse detergents or cell structure solubilizing agents inside the amputated arms. As the name itself implies, the leftover of such a decellularization process is a scaffold, or as they call it, extracellular matrix scaffold, which can be used for repopularization with amputee patient-specific cells, such as muscle cells, nerve cells, bone cells. The repopulated scaffolds are then placed in some type of a bioreactor to allow for composite tissue to mature under electrical stimulation in vitro. After confirmation of composite tissue formation, transplantation of the resulting biocomposite grafts took place to confirm perfusion and functionality in vivo. For ethical reasons, this second part of the technique, transplantation of thus generated bioartificial transplant grafts, cannot be performed on humans yet, since the technique in itself is still in its experimental stage. Although the primary part, perfusion, decellularization and repopulation of a human cadaveric arm, was indeed a success. To summarize this remarkable technique, the likelihood is very high that in the future those unlucky to lose their limbs will have their body-own limbs regrown in a bioreactor, and most importantly, without the need of an extensive immunosuppressive therapy after transplantation. And if you think this must be some science fiction, here is an interesting fact I promised you in the beginning. First successful thyroid and kidney transplantation was performed by French surgeon Alexis Carrel in 1908. In 1954, a Soviet surgeon, Vladimir Demikhov, successfully transplanted dog's head onto another dog's body, thereby generating a chimeric two-head dog with both functional heads. In 1970, an American surgeon, Robert White, successfully performed exchange transplantation of primate heads. And finally, a novel optimal vessel reconnection technique to be used in transplantation procedures was introduced by Chinese surgeon Xiaoping Ren in 2015. If you enjoyed this video, just hit the like button, click subscribe and activate the notification bell, because this helps me improve the quality of the content in the future.